This is lower in the sun's atmosphere, which you get to repeat us covering up, I'll just do it this way. This is from here in the sun's atmosphere, so you're looking at the lower layer of the sun's atmosphere. You can't miss the mass ejection event that's occurring on the right-hand side here. Truly dramatic event, one of the most dramatic certainly that I've seen. There's a solar flare down there as well. A lot of the material is raining back down, I'll just keep repeating it. And you are seeing a billion tons effectively being expelled from the sun here, and clearly there's a whole load of stuff going out into space as well. And of course the question to ask when you see events like that, and that is a particularly dramatic one, is, well, okay, we're sitting out there on the planet, that isn't actually us, that's a simulation of Venus. But of course, your planet and your spacecraft, whatever is subject to whatever is flying out through the solar system, this is Venus interacting with the solar wind, and people in the room who understand the physics of this better than me, but it's a nice illustration of the fact that you're subject to really what is thrown your way. So, in terms of coronal mass ejections, we're talking, as I say, about billion-ton clouds, 10 to the 12, 10 to the 13 kilograms of matter flying out at a few hundred kilometers per second. The fastest that we've recorded is something like 200 kilometers per second. You might get one a day, it depends on the time of the solar cycle. You do get them during the minimum phase, and you obviously get a lot more during the solar maximum. The principal drivers to many people of geomagnetic events, of course, are the coronal mass ejections. Of course, there's more to life than coronal mass ejections, but these are, in a sense, the major events. And as I've already hinted, there are shocks in front of a lot of these things generating energetic particles. So the problem is the thing at the bottom here. How do we track these things? How do you can identify sequences that, actually, I guess Jonathan showed something that looked very much like this, where for this is the 20-degree field of view. You can identify well, if you like, the nature of the inner heliospheric, or what we've never done before, because remember again, the sun is only down here, this is your 20-degree field of view, and the Earth is over here somewhere. Down here in the inner heliosphere, it is really lumpy. Yeah, lots of bumps, wiggles, blobs, whatever you call them, as well as the coronal mass ejection events. You can't miss them, there'll be one flying out in a second, surely there's one, an even bigger one, I think, will come out in a while. But basically, really quite a dramatic environment down there. And of course, it becomes more benign as you get out through the solar system. Something certainly hitting a spacecraft there, for example. There's a huge event. And that event that you've just seen is actually the one that came from that orange thing you saw earlier on from the Solar Dynamics Observatory, that huge eruption on the bottom right-hand side. We'll see some of that later on. Oh, we'll see it now, actually. That's the same event taken from our heliospheric imager instruments. So the sun is here, there's one of the coronagraph fields of view on stereo, but it's almost useless at that size. You have to shrink it down so you see the rest. So there's a 20-degree field here. The Earth is there. Stars and so on are removed, these different images again. You can see the coronal mass ejection coming out down here. That is a particular event that you saw a minute ago. Travelling out right through the heliosphere past the Earth, and actually it misses the Earth. You can see, you can't actually determine it fully from this image alone, but it certainly misses the Earth. But a beautiful display with these images. Now this is one that actually did hit the Earth. I stress, actually, see if I can remember the thing, yes. So again, Earth is at that point there, and this one you can see this mass ejection passing over the Earth. And this is from March 2012. I'd just like to stress this point again at the bottom here. If we're talking about facilities to track and image coronal mass ejections impacting the Earth, not single point measurements. I'm not getting at people with in-situ observations at all, you need both. But if you really want to see what it is that's actually flying over you, having an image along with your in-situ observations is a really powerful tool set, because you really know what it is out there that's flying out into space in that direction. And making observations from this Sun-Earth line is unique. And it really is where research is meeting applications. And I think it's important to just point out this thing here, which looks like blindingly obvious. You can actually see these events apparently passing over the Earth. And if from these images you can determine that they are passing over the Earth, we're not actually applying modelling here to actually see that. I'm showing you the data. The thing is actually passing over the Earth in these images here. So the question, if you like, to ask is, how can I determine whether the thing is in or out of the plane of the sky? That particular event generated an interesting auroral display. We excited the aurora. This is in Iceland. But you can also see up here, don't worry too much about the details necessarily, but energetic particles hitting the Earth the day before the arrival of the solar wind shock and a density pulse, which wasn't that dramatic, but and actually it's interesting to home in on the density here. Remember, we are imaging clouds here that have a density when they pass over the Earth that might only be 15, 20, 30 particles per cubic centimetre. That's why you're imaging, which actually in itself is quite an interesting thing to be able to do. Now, a lot of people in this room will be familiar with ENLIL. So basically with images such as these, or events such as these, I should say, people run the ENLIL MHD code to determine what is happening in the heliosphere, model what is happening in the heliosphere, using inputs usually from coronagraph data right up in the heliosphere. I should point out that what we're plotting here, this is code due to San Ostersil that is run by the Space Weather Prediction Center. So Sun is in the middle here, this is Earth, stereo A, stereo B on this particular plot. The ENLIL code has been run using, I think in this case, inputs from the Glasgow coronagraph to determine where it looks as though the CME, the coronal mass ejection, will fly out. This is plasma density up here. This image here is effectively what we see from the heliospheric imaging data. I think the most interesting thing to glance at, though, is the right-hand side. If you look at the green traces, those are what is predicted at Earth. It's predicted at the time of this line here, which is on the 7th at some point, and on the 8th, where the yellow line is, that's where the shock has arrived. And the trace here is predicted. Just remember that little jump there and that little, it's not so little actually, shock there. Those look very, very similar to the plots you saw on the slide before of the density and solar wind speed. But what I do want to show is this is a movie in a slightly different format, but it comes from the same code. So this is from ENLIL again, of the same event that you were looking at. I'll keep jumping back actually if they'll let me. I find this strange because if you look at it, Mars is moving backwards, but it's actually because the Sun-Earth line is fixed. I guess it's obvious which one is the Earth that's sitting there, of course. And you'll see the coronal mass ejection apparently come out over the Earth. And if you compare this image, that's effectively mimicking what we are seeing in the heliospheric imager. So this is MHD modelling, mapping or matching, if you like, what we're seeing in the heliospheric imaging data from the actual observations.
What's the significance of the red, the brightness of the red?
It's just density, I think, in that particular plot. Those are density plots, so it's just more dense, unless I'm misinterpreting that. Terry might have a better feel for that than me. But let's return to that if it's still relevant. I think that's just density, as in the plot at the top here. And that one is slightly more colourful, I guess, but that's what I think. How do we play games with this? Actually, games is the wrong word. How do I interpret it more effectively from the heliospheric imaging? If I take the heliospheric imaging data, and this is something Jackie in particular has specialised in, the Sun is sitting out here, you have your 20-degree field, and the outer field is sitting here. The ecliptic plane, the line here, if you like, is the line along which the Earth sits. If you take a narrow sort of opening angle from the Sun and you say, okay, I'm going to look at the intensity along that line, you can stack it in time. So you have a time plot along here with elongation. Again, this is degrees. This is going out to over 70 degrees here. And that line there is the outer edge of Glasgow, the widest coronagraph that we have. That is as far out as we get with coronagraphs, 30 solar radii across. So we're looking at the heliosphere out here. Now look at all that garbage flying out there. That fits with what we were saying earlier on about the nature of the heliosphere in close to the Sun. Of course, it simplifies a lot as you go out. This is the Earth here. Because of one of these plots, of course, the Earth will be a line that might change elongation slightly as you go through. But it is pretty constant in a sense. And where they cross, where you see a coronal mass ejection event apparently crossing that line, you're asking the question, is that hitting the Earth or not? Now these traces are important. If you think of a cloud of the sort that you just saw travelling out through space from the Sun, so you think a loop, if you like, coming out here, as it goes out along that red line, that red band there, you will see it as a curve here that has a steepness and a shape to it that depends almost purely on geometry. Of course, the velocity is relevant here, but a lot of it is geometry. Actually, just check what slide I've got next. Yeah, okay, go back. And the point about that is you can match, you can fit these lines. You can actually look at a line here, look at the profile of that line. mark some points along this line and fit a curve to it, or fit a shape to it that tells you something about where that coronal mass ejection is in or out of the plane of the sky. The whole point there is then you're mapping that third dimension. You then know where the thing is to some, obviously to some error bars associated with it, but the idea is to try to determine whether it's passing over the Earth or not. Take this one step further, J-maps as we call them, I haven't even mentioned that phrase yet, I apologise for that. We call these J-maps for several different reasons. Often these are sort of J-shaped, but they've also been developed initially for LASCO in 1999. I don't even remember the name of the person who originally did it, but Neil Sheely published it. But the chap that originally developed it with Neil, I think his initial was J, and on our side it's Jackie, so her initial is J as well. And these are plots here then at the top. These are data from our J-maps, if you like, for the events throughout, this is January, February, March 2012. So the event here that crosses the Earth at that point in March 2012 is the event you just saw. The bottom line here is Dusan Ostersil running the NL code to try to match, if you like, all events running through those 3 months. So this is the model data. Model data? Is that right? To compare to these things. Now you could look at the two sets and think, well, okay, there are some places where things don't quite match, but actually I think that the important point is to look at those and think there's an awful lot that does fit rather nicely when you compare these events to one another. And okay, there are things to tweak and model and work out and collaborate with and so on, but this is really exciting stuff, I think, really bringing the modelling and the observations together with heliospheric imaging. Now I think there's some important points here in that I mentioned trying to work out whether we're in the plane of the sky or out of the plane of the sky. Put CME there, but the CME has a star next to it, and that really it's for anything that moves out through the heliosphere. It could even be co-rotating interaction regions and the blobs that are entrained within them or whatever, but coronal mass ejections is what we're homing in on, of course. So imagine something moving out from the sun, and think of some geometry here where we have an observer, the sun itself, and something moving along this particular line at an angle phi. In the early days, if I can call them that, it was often modelled as a point. We call it a fixed phi observation, if you like. You model your coronal mass ejection front as a point, if you like, moving along a particular line. It's a blob at an angle phi. That angle, of course, can vary. And the plot down here, it's been produced by Jackie. If you think of the angle here, I should point out there's a paper here, where this is basically time elongation here, but they're offset with respect to one another, where we have traces for the different angles of phi. Basically, what it means is, you don't have to worry about all the details. The point is, you can see the shape of the profile in elongation time that you would expect for that blob that's moving out. And it's actually, you can see it's the middle one here, so it's the dashed dot lines here for those particular angles that actually fit that blob moving out along that line. But CMEs aren't blobs; they have a shape. They have a shape which is often determined, of course, by the magnetic structure, which is more like a loop shape. Okay, they can be rather unloop-like sometimes, that's a good word, but it's a good starting point, of course. So models developed using what we call a harmonic mean design, if design's the right word, where you had a big loop sort of rooted in the sun itself with a front out along this line. So you're thinking of an expanding circle rooted in the sun. Now, if you do that, you get a completely different, not completely different, but a different profile in the sense that, as you can see here for this one, for example, if you're looking at a circle moving out, you're not looking at the apex, you're looking at another edge to another part of that loop, so the traces will look different. And that's the other side of this nest in each particular case here, it's the dashed line. Now, what Jackie's done is actually produce something where we have what we call a self-similar expansion model, so you have a cone shape here, the angle is fixed, and you expand out a bubble here, and you can see the front of the bubble there, but the view from Earth, you can see where it crosses the circle here. And of course you can vary the size of your coronal mass ejection of your bubble. This is just geometry in a sense. And for each event you can plot, for the different angles, a whole nest of curves that you can then match to the curves you've seen on your J-maps. You've got lots of variables in here because the size of the CME is an issue, for example. But you have something that really gives you quite a powerful technique for modelling interpretations from the J-maps to determine where your coronal mass ejections are in the heliosphere and where they're going to go, even where they came from. So there's an awful lot of information that comes from this. And it gets worse in a sense because, of course, that all involved one spacecraft. So, of course, with two spacecraft, I'm not going to go into the same detail in this one, but if we take stereo A and stereo B and the sun sitting here, and you take your coronal mass ejection as a blob coming out, of course, you've got stereoscopic views. So you try to marry the two sets together to give you stereoscopic interpretations, which are one step beyond what you saw in the last slide just now. I refer you to a paper that's being published now. It's in press. So there's a really powerful set of techniques here to try to determine what is happening. Another thing I'm bringing before I get to the 5 minutes is that CME-CME interactions is something that's really coming to the fore in the sense that there's a well, I'll give you an example. This is from the 1st of August 2010, where actually 4 coronal mass ejections followed each other out in quick succession. You can see them on the J maps here, and even some curves that are fitted to them if you can see those lines. It's hard to pick them out here, although they are labelled in the different sequence at the bottom here. These are the same, but produced in a slightly different way. They're labelled L, M, A, and B, and don't ask me why. The interesting thing is there that the one that set off first, and if you're familiar with the J maps, you can see it down here. The second one followed it and seems to just wipe it out. In terms of the interactions of CMEs with one another, that gives you a lot of interesting things in terms of the interactions of these events, these magnetic clouds, and what the effects of those clouds might be, including the acceleration of energetic particles. And there's a whole host of events where we have these sorts of issues. It's being considered to be important enough to actually have a workshop in the UK in March of next year to try to identify these events and the importance of them in particular for energetic particle production. Let me just stress this is not an issue just for the Earth. For people interested in space weather, the Earth isn't the only thing that matters. We can study space weather using systems of the sort that I've been showing you for any target you like. Clearly, from our point of view, we have studies that involve the Earth, Mars, Venus, and so on. In this particular case, a classic example from early in the mission where a coronal mass ejection passes over comet Encke and literally whips the tail off. People have seen disconnection events where comets pass through sector boundaries and so on, but I think this was the first case where people really saw a coronal mass ejection interacting with a comet and literally taking the tail off. There's a nice demonstration of the fact that we can think about impacts on other sources. So I think the final points I'd make are these two. Stereo HI, the heliospheric images we've seen, I think have been a superb demonstrator of a monitoring concept, if you like. I think we can use it to understand how to best use such techniques in space weather context rather than a solar physics or space physics context, just science, if you like. They are unique. There's no other system like it at the moment. It gives us a great capability. And it isn't just the machine, if you like, and using that machine to understand where you would put such a monitoring facility in the future. It's also the techniques that I've been showing you, the geometrical modelling, utilising J-maps and so on, the use of the MHD codes, and even future instruments themselves, that I sort of stress at the bottom here, in terms of how you might apply an instrument like this within, say, the ESA's Space Situation Awareness Programme or something. It's of course something that's being discussed quite a bit. And as I mentioned much earlier on, where would you place such a thing in the heliosphere to be best suited to these observations? And of course, because stereo drifts away, you've got all the angles to investigate to identify which are the best positions and why. So lots of games like that you can play. So I think that draws me to a close. I'll just mention one other thing here. I should have put another bullet on here. And one of the big issues for us now is to develop a catalogue of events, which we have been doing. It's pretty near complete, but for the period of years that we have, and use that to really assess the value of these for space weather prediction purposes, because